Hey everyone, and welcome to today's Explainer. We're about to take a seriously fascinating journey, starting from the totally invisible world of molecules all the way up to massive real-world industrial applications. You know, chemistry is so often thought of as just a bunch of formulas in a textbook, but today we're going to see how it's actually the foundational blueprint of our entire physical world. We're going to trace how just a few basic atomic rules scale up to power huge manufacturing sectors. Let's get into it. All right, let's jump right in with a massive historical myth that literally held the field of chemistry back for years, the so-called life force theory. For the longest time, the scientific consensus was super restrictive. People genuinely believed that organic compounds had this mysterious life force inside them, meaning they could only be created by living organisms like animals and plants. This meant scientists thought it was fundamentally impossible to create these vital carbon-based compounds from scratch in a lab. It was a huge mental roadblock. But then, enter Friedrich Wöhler. In 1828, this guy brilliantly busted that life force myth wide open. While working in his lab, he actually managed to synthesize urea. That's an undeniable organic substance, but he made it entirely from ammonium cyanate, which is an inorganic compound. By pulling this off, he proved that the rules governing the non-living world and the living world weren't actually separated by some magical barrier. He single-handedly revolutionized organic chemistry, a real game-changer. So here's our roadmap for today's Explainer. 1. The Organic Revolution. 2. Exploring inorganic compounds. 3. The power of electrochemistry. 4. Ethiopian industry and environment. And finally, 5. The chemistry challenge question.
Let's kick things off with Section 1, the Organic Revolution, the Carbon Foundation.
So let's start with that very foundation Wöhler helped uncover. In organic chemistry, carbon is absolutely the star of the show, and chemists use different ways to represent these molecules. We use detailed physical models that show the exact geometric angles, like, that 109.5-degree angle in a tetrahedral carbon atom. And we also use condensed written structures to quickly communicate really complex chemical info. It's basically a specialized language we use to map out an invisible world. Now, the crucial point here is the structural difference between two major types of these organic molecules, saturated and unsaturated hydrocarbons. Hydrocarbons, just like the name says, are made entirely of carbon and hydrogen. If a molecule contains only single bonds between its carbon atoms, it's considered saturated. That basically means it's holding as many hydrogen atoms as it possibly can. Alkanes are your classic example here. On the flip side, if there's one or more double or triple bonds between those carbon atoms, well, it's unsaturated. Those extra bonds mean there's still room for more hydrogen if you were to break those bonds apart.
Moving right along to Section 2, exploring inorganic compounds, Earth's minerals.
By definition, inorganic compounds are basically the exact opposite of what we just talked about. They make up our Earth's minerals, the rocks, the ores, the non-living environmental framework around us. Generally speaking, the term refers to all compounds that do not contain carbon, but nature always throws in a few exceptions to keep us on our toes, right? Even though they contain carbon, substances like carbon dioxide, carbon monoxide, carbonates, and hydrogen carbonates are officially classified as inorganic.
And because this inorganic world is just so vast, chemists have this elegant way of grouping these compounds to make sense of them. We can classify them by the metals they contain, like your copper or aluminum compounds. Or we can sort them by their nonmetals, like sulfur or nitrogen compounds. And finally, we can group them by the chemical families they form, things like sulfates, nitrates, or carbonates. It's a super structured approach that helps us predict exactly how these minerals are going to behave in the real world.
All right, Section 3, the power of electrochemistry. Electricity meets chemistry.
Let's scale things up a bit and throw a completely new energy source into the mix. Electricity. This is a really vital comparison to remember because electrochemistry is very much a two-way street. On one side, we have voltaic cells. In a voltaic cell, a spontaneous chemical reaction just happens naturally, and we harness that reaction to produce an electric current. Think of the batteries in your TV remote. That's literally a voltaic cell in action. But on the other side, we have electrolytic cells. This is the exact reverse. Here, the chemical reaction will not happen on its own, so we actually have to pump electricity into the system to force that chemical change to occur.
And the reason electrolytic cells matter so much? Well, they are the absolute backbone of modern industrial engineering. By forcing chemical reactions using electricity, we can achieve some pretty amazing things that just wouldn't happen naturally. We use electrolysis for the large-scale production of specific metals and really vital industrial chemicals. We use it for electroplating, which is coating one metal with a thin layer of another for protection or decoration. And crucially, it's exactly how we purify crude metals that are mined from the earth into the highly refined materials we need for all our technology and construction.
Which brings us perfectly to Section 4, Ethiopian Industry and Environment, Macro Applications. Right here in Ethiopia, these exact chemical principles are what's driving our massive domestic industries. I mean, it's easy to look at a glass factory or a sugar processing plant and just see a bunch of machinery, right? But underneath it all, the whole shebang is purely applied chemistry. From the intricate inorganic reactions needed to produce cement for our growing infrastructure, to the organic chemistry involved in tanning leather and processing paper pulp, chemistry is the invisible engine powering the Ethiopian economy. Just look at the sheer, immense scale of an industrial furnace. This is a massive leap from those invisible microscopic carbon bonds we started this explainer with. To transform raw earthly minerals into products we actually use, we have to scale up those tiny test tube reactions into towering furnaces that operate at staggering extremes. This right here is where textbook theory meets the intense heat and pressure of the real world. For a perfect example of this extreme chemistry in action, let's look at quartz glass. Now, this isn't just your standard window glass. To manufacture this highly transparent, extremely high-strength material, Ethiopian industry has to take pure silica, which is essentially highly refined sand, and melt it down. But it doesn't melt easily. It requires a staggering temperature of about 2,300 degrees Celsius. Once it hits that state, the molten, viscous liquid is poured into molds. It's just a beautiful demonstration of using extreme thermal energy to force inorganic compounds into entirely new, incredibly useful forms.
And finally, Section 5, the Chemistry Challenge question. Test your knowledge.
All right, we have covered a ton of ground today, from micro-building blocks all the way up to macro manufacturing. So now it's your turn to apply what we've learned. Here's today's challenge, pulled straight from our organic chemistry section. Think back to what we discussed about saturated hydrocarbons. You know, those molecules with only single bonds that are holding the maximum possible number of hydrogen atoms. If you have exactly 8 carbon atoms in that chain, what is the full chemical formula going to be? Use those rules of alkanes we talked about to figure it out, and please comment your answer down below to see if you crack the code. And as you go about your day, look around and ask yourself what invisible chemical reactions made all of this possible. Thanks so much for joining me on this explainer, and I'll catch you in the next one.